So hello everybody, we talk about the mixer part of this do-it-yourself transceiver. You see here on this picture the transceiver built up on my bench. The antenna input is on the top left corner. You have a little antenna amplifier we already discussed. We have the bandpass filters we have already discussed. And now the signal gets transferred to the mixer board. We have 3 mixers on this board. The first mixer is mixing down the receiving signal to 9 MHz intermediate frequency. This intermediate frequency then gets filtered by the crystal filter and then comes back and gets product detected, demodulated by the next filter, by the next mixer, and then gets transferred to the audio frequency audio amplifier down out to the loudspeaker. And then there's a third mixer, and the third mixer mixes the intermediate frequency of 9 MHz and transfers this signal, so mixes it down to 300 kHz, and this signal gets then AD converted in the microcontroller, and this microcontroller then performs the FFT analysis over a range of plus minus approximately 100 kHz to show the spectrum of the frequency band, the ham band that we are currently working on. So these 3 mixers we are talking about today. And mixing signals means nothing else but multiplying 2 signals. If you multiply a sine wave with a frequency 1 omega 1 t, and you multiply it with a signal with a frequency 2 omega 2 t, what you get is a signal half the amplitude, but with a component with frequency 1 minus frequency 2 and a component with frequency 1 plus frequency 2. So this is typical analysis stuff. And this is mathematics, and that's really something you can use if you have a signal on frequency 1 and you would like to transfer this frequency down. If you receive a satellite signal on, I don't know, 25 gigahertz and you want to transfer it down to a few hundred megahertz, you have to mix it with a second frequency, and with this second frequency you can mix the signal in a new frequency range, in a frequency range that you would like to work on. You don't lose the information of the first signal. The modulation information is still available, and you have that available even also in the mixed signal. So we use that often in electronics, especially of course in radios. And there are all kind of different mixers out there. And one passive mixer that's very often used is the diode ring mixer, often also called the double balanced diode ring mixer. Diode ring mixer because these diodes are in a ring form organized, and double balanced because the input is imbalanced and the output of this transformer is then a balanced output, and the same over here is a double balanced ring mixer, diode ring mixer. You can mix 2 signals together also on a PN junction, especially with a BJT transistor. We talk about that a little more. This is what you use today in these active mixers that you can buy from all kind of vendors. And of course, more and more popular is you just sample your 2 signals, and then after the sampling of sine omega 1 t and after the sampling of sine omega 2 t, you just work with a digital representation of these signals, and you can do all kind of math with it. And of course then use a DAC to regenerate the mixed signal. So there are these methods, And maybe what's interesting, if we take a closer look at these active filters, these are the filters that you usually use today, because these passive filters, you have a pretty high attenuation. You need an amplifier before or after or on both sides of this mixer to have a reasonable signal level to work with. It's easier than with these solid state mixers. They usually have also an amplifier on board. And now what's interesting is, if you look at this sort of configuration, you can explain the way transistors can be used to multiply the best in this configuration here. You know that the collector current of a transistor is a saturation current times e to the power of VBE, V base emitter, divided by VT. VT is a constant in the PN junction, and based on the material, silicon material that you're using. And this is typically 26 millivolt at room temperature. And saturation is the saturation current, also defined by physics. But you can see that IC is an exponential function of VBE, e to the power of VBE divided by a constant. And if you mirror IC1 and IC2 through a common current source, IEE in this case, then you can show that, and you have two input voltages, the input voltage V1 from base of the transistor 1 respect to the base of the transistor 2, and the other way around. So this is VE1, and V2 in this equation is nothing else but minus VE1. And you take the difference of these two currents, you can show that this is the current of the current source times tangent hyperbolicus of V1 divided by 2VT. And you know, for small angles tango hyperbolicus x of a small angle is equal to x. So you see that this is for small signals of V1. You get you get a multiplication of IEE times V1. And if you change now IEE, instead of having a constant current source like in this example, if you change IEE into a voltage variable current source, and that's what you have here. This Q3 and Q4 is nothing else but a current source which is voltage dependent. And if you replace IEE by this voltage dependent current source, what you can see then is that you get a signal delta. The delta of the collector currents here is nothing else but V1 times VB, okay, minus VBE, but this is actually a multiplication of V1 and V2. So you have a multiplication of two voltages. In this case, this multiplication only works in 2 quadrants, because this V2 always has to be positive voltage. And what you have to do is you just have to copy this and mirror this and make a second multiplier like this one in parallel, and reconfigure it in a way that you can work with negative voltage as well. And then you have all 4 quadrants. You can multiply positive and negative voltages on V1 with positive and negative voltages on V2. And this is then called a Gilbert cell, and that's the basic fundamental circuit that you find in all these active mixers nowadays. The diode ring double balanced mixer is nothing else but actually switching the input voltage, the input signal RF with these diodes. The diodes, the purpose of these diodes are switches. They are used as switches. So you bias these 2 diodes, D1 and D2, in a way that they are conductive, and D3 and D4 are high impedance. and then you switch back and you make D3 and D4 low impedance and D1 and D2 high impedance. So you can use these diodes as switches. You usually use Schottky diodes because they have a low forward voltage. Ideally, you would use devices with 0 voltage, forward voltage, and so you can switch perfectly at the 0 crossing. And actually, you can do that. You can, instead of these diodes, use also analog switches and then switch with a rectangular signal and switch them at the even more precise than with these diodes. Anyway, they have a low on resistor and a good high frequency response. So they're very small, very little stray capacitance, and so these are good diodes to use. You have to have a significantly higher LO signal than the RF signal, because otherwise you start switching also the diodes with the RF signal. You don't want to do that. You want to have a leading voltage or a leading signal here on LO. Make sure LO switches these diodes and not RF. So go a little bit higher or significantly higher signal on LO than on RF. And of course you have to have a certain minimum level of signal to get the thing going, to overcome the 0.3 volt and so on. So that's explained down here, what I've just said. You see these inductors. There's only one inductor in use at the moment. There's never both inductors used in this kind of configuration. I made a simulation of this diode ring mixer in LT-Spice. LT-Spice is a really nice tool. It has a bit an old-fashioned graphical user interface, but the SPICE models behind these components are very good and are not better or worse in other more sophisticated SPICE simulators. So I'll use this LT-Spice. It's straightforward and simple and fast. So anyway, you see these 4 diode rings with these 4 Schottky diodes and the 2 transformers, and then the 2 signal generators with the output and input impedance, and then a load impedance of 50 ohms at the intermediate frequency output. This is the signal, the output signal, and you see a period of a 9 megahertz input on RF. So I did choose 7 megahertz input on RF, and you see on a 2 megahertz period the switching of the RF signal through the diodes. And if you look at the FFT spectrum, you see the 2 main components. You see 5 and 9 megahertz, and of course you see also some other frequencies that you get when mixing the signal. You have some feed through of LO, you have some feed through of RF directly without any mixing to the output, and you have all kind of intermediate and other mixing products. And this is really a tricky thing. You have to make sure that you have a perfect impedance matching over all these frequencies at the output. Not only at your desired and interested frequency, in my case at 9 megahertz, you should make sure that you have a broad matching of the frequencies. Here, a broadband matching of the intermediate frequency. Otherwise, you get reflections back, and the reflections get mixed with the input frequencies again and signal again, and then goes back and forth, and you get all kind of crap and other spectrums that you don't really want. I also did a simulation in Canoe Radio. Canoe Radio is a free tool you can download. It's also very simple to learn, and you can simulate all kind of interesting radio stuff. and even attach hardware to it and do some signal analysis on top of it. We have two signal sources here at the input. We have the 7 megahertz RF input, we have the 2 megahertz LO input, we have this multiplier, and we display it in the time domain, and we display the multiplied signal in the frequency domain. Let's take a look at that, how that works. Here you see the result of the simulation. On top you see a slider adjusted to 7 megahertz for the RF, and you have a frequency range LO currently at 7 megahertz, 2 megahertz, currently at 2 megahertz, and you have down here the spectrum. Okay, and that's not a big help here, this time display, but you can look at the frequency spectrum. And if we change, what do you expect if we change the LO frequency, let's say to 3 megahertz? And you see that it is now mixing the signal with 3 megahertz. 7 megahertz plus 3 is 10, 7 megahertz minus 3 is 4. And if we move it LO down to 1 megahertz, so here we are, and then we get 8 megahertz and 6 megahertz. And you can go the other way around. You can go here to 7 megahertz. You make out of LO RF and out of RF LO, and go down to 2 megahertz approximately here, and we are back at 9 megahertz and 5 megahertz. So you can interchange LO and RF, and you should get exactly the same result. If you have a 7 megahertz input in your radio and you have an intermediate frequency of 9 megahertz, you have to up convert it from 7 to 9. If you have on 20 meter a 14 megahertz signal and you need to convert it to 9 megahertz, you do a down conversion from 14 to 9 megahertz. So that's all it is. What happens if both frequencies are exactly the same? In this case we have 2 megahertz and 2 megahertz. What we get is 0, plus or minus 0, and 4 megahertz. And SDRs are also called zero frequency mixers, because you mix the signal down to NF into the audio frequency range, and you can detect and demodulate here on the audio, in the audio range directly. And yeah, you can play around. Why don't you just download this tool and build up your own Canoe Radio simple mixer? And I think it's time to move on and then take a look at these mixers on the bench. Let's take a look at two passive mixers and an active mixer, and we want to test them out and see how they perform and compare them to each other. The first mixer that you see here on the bench is an SBL1 from Mini Circuits. SBL1 Mini Circuits device, good for 500 megahertz, and it's a passive design, the same design that we discussed before in the PowerPoint presentation. And the second mixer we take a look at, also a passive mixer, is a homebrew. Let me see here. Is this homebrew mixer? I can show you this mixer a little closer. This is exactly the same that how the SBL1 is built up. You see the two toroids with the bifilar windings, And you see maybe even the 4 Schottky diodes here in the middle. Here, that was a nitty-gritty work, but you see here the 4 Schottky diodes in the ring form, and you have the 3 connectors, the 2 inputs and the intermediate frequency output. And then the third mixer we take a look at is this one here. That's an active mixer. It's a 8831. So it should focus now. And that's very nice design, a very nice mixer. It has some amplification in it, so you compensate for the loss that you usually have in these analog passive mixers. And that's exactly the one that I'm using in my radio down the road. I have 3 of those in the radio. One for the intermediate frequency of 9 megahertz. The other one I use as a product detector. And the third one is used to convert this 9 megahertz intermediate frequency to 300 kilohertz for the input to my analog digital converter, and then use it, make a spectrum analysis on top of it with a fast Fourier transformation. So let's start with this analog SBL1 mixer. Let me see. What we have here is the RF input, the LO input. I have 7 megahertz RF input here, a 2 megahertz LO sinusoidal input here, and this is the intermediate frequency that we want to measure. And you can see here on the scope, that's the intermediate frequency, the output. I have a 1 volt peak each signal for RF and LO, and this is the output. And you see that's pretty much what we have seen on the SPICE simulation as well. You can see the main 7 megahertz signal, and which is clocked and chopped with the 2 megahertz LO frequency. And now, of course, I could take a look at the fast Fourier transformation here on my scope, and you would see a 9 megahertz peak and a 5 megahertz peak. So you have this 7 megahertz plus 2 is 9, 7 megahertz minus 2 megahertz is 5 megahertz. But you don't see any of the harmonics, a few harmonics you see here. So it's much nicer to take a look at this signal at the pretty good real spectrum analyzer in my Sigland here. And you see this same again. You see this 9 megahertz signal, that's what we really want. And you have a 5 megahertz signal down here. And this is 5, 6, 7. So that's the input. And you have 0, 1, 2 megahertz, that's the LO. If I just disconnect RF, if you disconnect RF, you see a 2 megahertz LO pushing through all the way to the output. And there, you know, ideally this would be 0. And if I disconnect LO, then we have a 7 megahertz pushing through to the IF. But it's pretty much attenuated. So let's connect then the homebrew mixer, which is down here. So this is connect RF. So let's take a look at the scope. Pretty much the same, a little higher amplitude, but you can see again the 7 megahertz pushing through and again chopped off. So it's rather similar. And if I switch over to FFT over here, You see again 7 megahertz and 9 megahertz and the 5 megahertz peak, and on the scope again. But you see also we have a few more cross products, and you see that we have a more feed through of RF and LO and cross mix products. If I just disconnect again RF, then you see this is LO, and this was much better with the SBL. So you have LO, so the 2 megahertz input, you have it again at 4 megahertz, 6 megahertz, 8 megahertz. So we don't like that, because these products get mixed again, maybe reflected even. And if you don't have a proper termination of your mixer, and all these spectrums should be terminated by 50 ohms, and if they are not terminated by 50 ohm, so you should have 2 megahertz terminated by 50 ohm and maybe 20 megahertz as well. And if those are not perfectly terminated, then they reflect back and get mixed up with and remixed with other signals that are around. And so that can cause some problems. So the SBL was definitely better there. I disconnect now LO, and we have a pretty high feed through of RF now. This is 7 megahertz spectrum. But it works pretty well. I mean, I could use this. I could use these mixers in my radio, and I tried that before, and that works pretty well. Of course, you have to have an amplifier before or after this mixer, because you have a pretty high attenuation, even 10 dBs. And good. Now let's hook up the active mixer and see how that performs. So the 8831 mixer is hooked up. Again with 7 megahertz RF with 2 megahertz LO. I had to reduce significantly the voltage input. I had before between 1 and 2 volts peak for RF and LO, and here we have only 100 millivolt, because you have active amplifiers in this mixer. If you take a look at the voltage on the scope, it looks really nice, as it should be, and it's performing really well. However, we have almost 100 milliamp current drawing, and so this is certainly not a low power device at all. I have 3 of those mixers at 300 milliamps right away for the radio, without any other electronics. So that's a lot. And on the spectrum, you see again the 9 megahertz spectrum and the 5 megahertz spectrum as expected, and a few harmonics, relatively a lot. Let me take off the RF signal, and here we have the LO. LO is at 2 megahertz, and then at 4, 6, 8 again. This is similar what we saw on the homebrew diode ring mixer. And now I take off the LO signal, and then we only have this 7 megahertz that's getting through. Well, so overall I like these mixers. They're simple, easy to use, nicely, and easy to configure. All right, that's for the mixer stuff so far.